Today we're going to take a closer look at the different types of plate boundaries. Remember that the Earth's crust is cracked and it's divided up into these sections that we call plates. And those plates are floating on the hot rock of the mantle underneath, and so they slowly move around. So we're going to take a look at what happens along all of those boundaries, the borders where two plates come together. You'll need a copy of this page to complete as we go, and here are the materials you'll need as well. You should have graham crackers, a fruit roll-up, some wax paper to lay down on the table, some icing, and the icing is vanilla flavored, but it's got red food coloring in it, paper towels or napkins because it can get a little messy, a small bowl of water because you will need to dip one graham cracker quickly into some water, and a pair of scissors for cutting the fruit roll-up. As you do this lab, you can go ahead and eat the leftover fruit roll-up, any of the graham crackers that are left over. If your icing has been sitting out this whole time and has not been put in a refrigerator, then you really shouldn't eat it. If you did put it in a refrigerator, then just make sure it's at room temperature, not super cold when you start this experiment. And if you did refrigerate it, you can go ahead and eat it. So to set this up, you're first going to need to create some oceanic crust, and that's going to be represented by fruit roll-ups. So fruit roll-ups are thinner, and so that's what we're going to use for our oceanic crust. So you want to go ahead and cut those. The graham crackers are going to represent our continental crust, our land crust, because it's thicker. When you cut your fruit roll-up, you want each one, you need at least 3 squares, and they need to be about the size of your graham cracker, but it doesn't have to be perfect. As long as you've got rectangle-ish squares of fruit roll-up, that's great. Don't stress if it gets stuck together. And it is easiest to cut it while it's still attached to the plastic, and then go ahead and peel it off of the plastic once it's cut. So now take your icing and go ahead and spread it onto your wax paper, and start with about 2/3 of it on the wax paper because as you pull things off of your icing, you might need to add more icing as you go. So start with 2/3 and then you can pull from it more and spread it out more as you go through the experiment. So you want to go ahead and spread that out with a knife. By the way, make sure your wax paper is on the shiny side. There's a shiny side and a dull side. The shiny side will help things move easier. And then go ahead and spread it out so that it's about the shape of a graham cracker size. Now let's take a look at the different types of plate boundaries we have. Where these plates border one another, they're moving at a rate of about 2 inches a year, really slow. But they can move in 3 different ways. The plates can be moving towards one another, which we call convergent. They're coming together. The plates can be divergent. They're dividing away from one another, so they're headed in opposite directions. And then the plates can be sliding past one another, which is what we call transform. So we have these 3 types of plate boundaries based on the movements. And we're going to take a moment to look at each one and go ahead and create simulations of those with our icing, graham crackers, and fruit roll-ups. So let's take a look at our convergent plate boundaries first. In all of these, what we have in common is we have one plate from the left working its way and headed towards the plate on the right, and so they're going to collide with one another head on. But we have 3 different kinds of convergent plate boundaries because we have combinations of the different kinds of crust. So we can have a continent plate converging or coming together with a continent, an ocean coming together with a continent, or 2 ocean plates coming together. So we'll take a look at each one of those separately. We're going to start with our continental versus continental plate. So we have a continental crust over here, that's land, coming together with another piece of land. And what they're going to form are mountains. Mountains, fill that in that box at the top, mountains. So first I'm going to show you the computer simulation of this. So I have a continental crust over here, and it is pushing up against a continental crust on the other side. And you can see that the land itself starts to kind of fold in on one another, and it gets higher. So it's actually pushing up to form these mountains. So the crust is getting destroyed, folded in on one another, and raised up to form mountains. Now let's go ahead and try it with your actual graham crackers. So when we do this, if you just took your graham crackers right now and pushed them together, they really wouldn't do anything that exciting. So we are going to soften one graham cracker up so that the graham crackers will actually fold the way that real land would be like crushed and folded in. So to do that, you're going to need to get one graham cracker wet, and you literally want to dip it in for like 1 second. Make it pretty quick. If you dip it in longer than that, it will dissolve pretty quickly and you'll just be left with a bunch of crumbs in the water. So no more than 1 second, dip it in your water, pull it out. And then go ahead and lay that graham cracker that's wet, you can see mine's on the right here, against the graham cracker that's dry so that they're lined up end to end. Now go ahead and watch my simulation first, and then you can go ahead and do it. I've got my continental crust pushed up against my continental crust. And as I push them towards one another, that land that's in the center is going to go ahead and fold over and raise up. And that's exactly what happens in real life to create our mountains. So go ahead and try that. In real life, there are several tall mountains that were formed this way. The most famous of all is Mount Everest. Mount Everest is the highest mountain in the world, and it is formed from two convergent plate boundaries that are pushing against one another, and it's actually growing at a rate of about 2 inches a year. Now let's take a look at an oceanic crust converging with a continental crust. So water converging with land coming together. So we have an oceanic crust in this diagram on the left, coming together with a continental crust over here on the right. And it's going to form two landforms. The oceanic crust is heavier, so it's actually going to sink down. So even though it's thinner, it's covered with water, and so it's heavier. So it will sink down, and it actually goes underneath the land. So where that happens, there's going to be this long, narrow gap called a trench. And then as that rock gets shoved underneath, it will create extra heat and pressure that will break through the surface to create a chain of volcanoes on land. So the two landforms formed here are a trench and volcanoes. Let's go ahead and take a look at the computer simulation to understand what's going on. So again, that oceanic crust is heavier, so it sinks underneath. And as it does it, there's extra rock down here. So now there's solid rock and it starts to melt, and it creates all this extra pressure and heat right here in friction. So as it does that, that heat will eventually break through the crust here, create little hot spots. And as it creates that extra pressure, it'll burn a hole through the crust and create those little gaps. And that's where we get these chains of volcanoes that form. So let's go ahead and try it with your actual graham crackers. Pull off the graham crackers from before, smooth out your icing, and now you're going to go ahead and lay down an oceanic crust, that's your fruit roll-up, against your graham cracker. And you notice the difference in height there. The oceanic crust, though it's heavier, it's more dense, is actually thinner than the land. The land kind of raises up because it's lighter. So this is a little messy. When you do this, you want to lift your continental crust up a little bit so that you can shove the oceanic crust underneath it. And that when it shoves underneath, we call that subduction. It's going underneath, being subducted. So the oceanic crust is actually getting destroyed as it gets shoved back down into the mantle. A classic example of an oceanic versus continental crust is Mount St. Helens. This is a famous volcano in Washington State, so in the northwestern part of the United States. And behind this is Mount Rainier. Those are two volcanoes here in the United States formed by a plate in the Pacific Ocean that's shoved down and being subducted underneath the continental plate of that land in Washington State. Our last type of convergent plate boundary is oceanic versus oceanic. So these are two oceanic crusts that are coming towards one another. And inevitably, when those two crusts come together, one of them is going to be a little heavier than the other. Maybe it's just bigger, or it's got more rock on it, or it's a deeper water. For whatever reason, one crust is going to be heavier than the other, and that is the one that will sink down, and the other crust that's lighter will rise up. So we get those same land formations that we did with an oceanic versus continental. We'll have a trench, and then we'll also have underwater volcanoes that form. And I'm going to introduce to you a new word that we use for underwater volcanoes. They are called seamounts. S-E-A-M-O-U-N-T-S, seamounts. And you can guess kind of why they're called that. They're under the sea, and mounts is short for mountains. So these are actually volcanoes that are underneath the ocean, and not ones that we can see here on land. Now, I will tell you, I actually tried doing this one, pushing 2 fruit roll-ups together, and what I got was a big, ginormous mess. So I'm going to have you completely skip trying to make this one with your icing because it was just too messy and it didn't work out very well. So instead, I'm just going to go ahead and show you the computer simulation. So we have a heavier oceanic crust over here sinking down underneath. And as it gets shoved down here, the rock that's here is getting destroyed and melted. It's creating all this extra friction and heat and pressure. And so that creates this hot spot in the mantle. And that will eventually create these volcanoes. So of course we have our trench, and our trench actually forms, let me back it up. Our trench forms right away. And then over time, that extra heat and pressure will create a hot spot on the crust where it's just hotter, and that will eventually bubble up, you can see, and break through. So we get volcanoes, and at first those volcanoes are underneath the ocean. Given enough time, some of them will grow above the ocean floor surface and become islands. All right. A good example of a trench is the Mariana Trench, which is the deepest place on Earth. And so this is found in the Pacific Ocean. And this trench over here is actually a real picture that I found from a guy that went snorkeling in Iceland. Iceland is right along that trench boundary, and so there's a nice deep trench, and he was actually able to take a picture of it underwater. Pretty cool to look at what they look like. So those are trenches. As I mentioned, it will also form seamounts, which are volcanoes underneath the ocean's surface. Given enough time, as I said, those will erupt and eventually develop enough lava to come above and break above the ocean surface to form islands. And the most famous example of that would be the state of Hawaii. The state of Hawaii is a series of several volcanic islands. So they were formed from seamounts that erupted and got tall enough to actually become land. That's all convergent plate boundaries. Now let's take a look at divergent plate boundaries. This is where the Earth's crust is separating away from one another. So they're dividing away from one another. And we have 2 types of divergent plate boundaries, continental versus continental, and oceanic versus oceanic. So let's take a look at the continental one first. We have 2 chunks of land, and they're going to be separating and dividing away from one another. As they move away from one another, they're going to form what's called a rift valley. The word rift really actually means like a separation. So if you have a rift with your friend, it means you had a disagreement and you separated. And valley means a low area. So a rift valley is what they form. Let me go ahead and show you the computer simulation here so you can see and visualize it. So what we end up with is this low-lying area in between 2 higher areas. So the original continental crust, when you started, the original continental crust was higher up. And then as it separates, where this gap is, we actually have new magma rising up and hardening and cooling to form actual new land. So there's actually new land, and these are growing. So they're getting wider and wider year by year. And some of them will actually fill up with water and create like a long skinny lake, depending on how low down that area is. Some of them will just be land. So let's go ahead and try it with your graham crackers. Take off your previous graham cracker and fruit roll-up. Smooth out your icing, add more if you need to, and go ahead and put your 2 graham crackers side by side. And it really doesn't matter whether those little lines are horizontal or vertical, as long as you've just got them side by side. So let's go ahead and take a look at what this looks like. I'm going to go ahead and pull my continental plates away from one another. And notice I've got this high land here, which is the original graham crackers, and then I've got this low-lying area in the middle. That would be my Rift Valley. So a good example of this is the Great Rift Valley in Kenya. So actually a whole lot of Kenya has, actually a lot of Africa has rift valleys throughout it. It's got a lot of divergent plates, but this one is a huge rift valley. And you can see it really looks just like your graham cracker crust did, where it's spread apart and it's got that high area and some low area in the middle. And yes, it is actually growing. So the rift valleys are getting bigger and wider and farther apart every year. Now, usually you can't actually see a big crack in the earth where magma is actually coming up because it's kind of clogged, and so it's clogged over with miles of land above that little opening. But there is new crust being added as that magma cools and hardens underneath, and so the land is continuing to split apart. Now let's take a look at divergent plate boundaries for oceanic versus oceanic. So we have two plates that have ocean above them, and they're going to be splitting apart from one another. And what they're going to form is called a mid-ocean ridge. Mid means it's in the middle of the ocean. Ocean means it's in the ocean. And ridge means an area of raised land. So let's take a look at that with our computer simulation, a mid-ocean ridge. The computer really doesn't look that exciting. We have them, you can see that they're spreading apart, but they're filling up with water, obviously, since it's under the ocean. So it really doesn't look that different. But the sea is actually growing at these places. We call them seafloor spreading. It's where the seafloor is actually spreading and getting larger. So to make this, we're going to go ahead and take off the graham crackers from before, smooth out our icing, and put two fruit roll-ups side by side. Now, the first time I tried to make this video, since my fruit roll-ups are red and my icing was red, it was really hard to tell the difference between them. So I actually started with some new vanilla icing that didn't have food coloring in them, so that it was a little clearer on my video. It's still kind of messy though when I did this. So you're just pulling those apart. And as you do that, it doesn't pull out real smoothly, especially my icing was a little too thick. But you can see that I've got this little area where the crust is growing. We have more crust coming up from the mantle, and it's hardening and cooling. That magma is hardening and cooling to form new land. Now, before we get to specific examples, I just want to show you this three-dimensional map. This is actually a map that's hanging in my living room. Believe it or not, it's a big three-dimensional map of the Earth's oceans, and I love it. I think it's so cool to look at, so it's hanging in my living room. But it shows three-dimensionally these mid-ocean ridges. So this is the mid-ocean ridge here in the Atlantic Ocean. It's this huge, it looks like a big scar running across the ocean. This one is in the Indian Ocean, so to the east of Africa, south of the country of India. There's another one, and then there's also one in the Pacific Ocean. If you were actually able to go down and see one, which you really can't, they're too deep down, but if you were able to go see one, they would kind of look like this. So you'd have this gap where you've got magma that's coming out, and it's creating these little raised areas. So here is an actual picture of the mid-Atlantic ridge, and this is taken right along Iceland. Iceland is right in the middle. It's an island that's right in the middle of this divergent plate boundary in the Atlantic Ocean. So this particular line of underwater mountains is called the Mid-Atlantic Ridge. For obvious reasons, it's in the Atlantic Ocean, so we call it the Mid-Atlantic Ridge. And it is the largest tectonic plate formation in the entire world. It is literally thousands and thousands of miles long, and it's just these jagged openings and raised areas underneath the ocean. Now let's take a look at transform plate boundaries, our last type of plate boundary. In this case, the plates are not coming together, they're not separating, they're simply sliding past one another. And you do have transform plate boundaries with continental crust. You can also have them with oceanic too, but it really looks the same for both of them, so I'm just going to give you the continental example for it. So we have two continental crusts sliding past one another, and when they slide past one another, they create what's called a fault. It's like a crack in the Earth's crust. And that line that you can actually see on the Earth's surface is called a fault line. So that's what it's called, a fault line. So let me go ahead and show you the computer simulation of it. When you look at this, you can see that they're sliding past one another, and you can see that line. Now, a lot of times when you first look at it, it looks kind of silly. It looks like, goodness, there's going to be these big gaps opening up in the Earth's crust. But that's not true. We're only looking at these two plates in the simulation. In real life, there would actually be a plate here in front of this side that this plate is diverging away from. And over here, there's another plate out in front that it's converging on. So remember, it's like a 3D puzzle. So though this simulation only shows those two plates, there's actually going to be ones in front and behind the others. So it's converging and diverging on the other plates around it as it slides past the one in front of it. So to do this, I did actually take a graham cracker and break it in half, kind of on a jagged edge, because that's really what it would look like in real life. In my computer simulation, it shows it as like this nice, pretty line. In my diagram, it shows it as a nice, pretty line. But in reality, rocks don't perfectly divide up that way. Usually that's kind of jagged. So as I push down on this one, I'm going to move it back and forth. Usually it just goes one direction, but it does kind of sometimes shake back and forth. You can see that there's little crumbs of the graham crackers that are breaking apart on that transform plate boundary. So the fault lines, some of them you can't actually see on the Earth's surface, but some of them you can. One of the most famous ones here in the United States is called the San Andreas Fault. The San Andreas Fault is in California. And if you were flying in an airplane and looking from the sky, you would see it as this big crack that's running across the desert area of California. That's what it looks like from way up in the air. If you're a little closer down, zooming in on it, it looks like this out in the sand. So you can actually literally see the gap in the Earth's crust. Now, as you can imagine, when those are sliding past one another, let me just move back to our simulation. As those are sliding past one another, there's some tension there as the rocks push against one another. There's friction. Rocks aren't exactly nice and even and smooth. So what ends up happening is along these transform plate boundaries, we have earthquakes. And here is another one of those. You can actually see there was an earthquake along this. This is part of, it's not the San Andreas Fault, but it's another fault in California where you can see the little gaps that create and the damage that happens from earthquakes. So earthquakes are exactly what they sound like. The earth is quaking or shaking back and forth. When you have earthquakes along these faults, you also can have the rock layers shift. So if you take a look at these rocks, it used to be one layer that was all like nice and neat and lined up. So this part right here used to be, see how it matches this section right here? So this rock layer used to be connected to this rock layer, and this rock layer here used to be connected to this rock layer. So it used to be like nice, pretty lined up layers of rock. But now because we've had a plate boundary, a transform plate boundary, the rocks themselves have actually shifted. And so the layers of rocks have shifted and they're not lined up anymore. Let me also just show you real quickly, we didn't have this as a diagram, but here's an oceanic versus oceanic transform plate boundary. And again, it's the same thing. You're going to have a fault line that happens and you can have earthquakes happen. And the only difference with if it being oceanic and oceanic is that if you do have an earthquake there, unfortunately that earthquake, as they shift past one another, is going to create a whole lot of energy that's released up into the water. And so underwater earthquakes that happen along those oceanic fault lines can cause what's called a tsunami. And a tsunami is basically a huge, huge wave. You know, regular waves are caused by gravity and changes in the temperature of the water, but a tsunami is caused by an underwater earthquake, and they actually can be really, really devastating. So the earthquake hits, and then it creates this huge energy of wave, and however far away that earthquake was from land, it will rush out on that land. This is a picture of one that happened in Japan and caused a whole lot of devastation and wiped out a whole lot of communities.